The second part of my talk will be on mainly on natural greenhouse effect and on the natural ozone hole. Although with ozone hole I will also mention the anthropogenic part with freons, connected with freons and other gases which have been emitted into the atmosphere in last decades. In last decade, no more. More on natural than on anthropogenic, because the anthropogenic will be your task. Nowadays, very actual greenhouse effect and greenhouse gases. Not everyone knows that the most important greenhouse gas is water vapor. Approximately 60% of the whole greenhouse effect is provided by water vapor in the air. Some 26% of greenhouse effect is provided by CO2, some 8% by ozone, 6% by methane, and the nitrous oxide. And here on the graph you have increase of CO2 concentration in the atmosphere in average. This is from Mauna Loa Observatory in Hawaii, far from the local sources of SO2. You see the increase of... Yesterday I made a new version of this presentation, but I do not find it. So this is the old one, and you see that a lot of data is missing, some decade and a half. So I had to use the old one. You see ups and downs. This is vegetation. During the summer period, the plants are eating CO2. During the winter period, they are not. So it goes up and down. But there is also a trend up, which is the top story of Al Gore and also of some other concerned people. Not only greenhouse gases, but also the aerosol have impact on greenhouse effect. Aerosols, opposite to the greenhouse gases, in general diminish the heating of the air, while this is the albedo, the reflectivity of the Earth, is decreased by grayish or white smoke from the volcanoes. How the greenhouse gases work, I do not know which professions are you. I will try to explain it very shortly. Three atomic molecules and 4 atomic molecules and 5 atomic molecules can vibrate like 2 H's and 1 O for water vapor. If the photon of the light hits, or infrared light hits the molecule, it starts to vibrate. And this is called absorption of electromagnetic energy. In infrared, it goes mainly by vibrations and by rotations in infrared. When the molecule stops to vibrate, this energy must go somewhere, and it is emitted from the molecule out again by a photon, by energy of electromagnetic waves. This is so-called emission. And so as we have 3 atomic gases in the atmosphere, the infrared radiation which is emitted by the ground hits the molecules of 3 atomic gases which start to vibrate, and this energy does not go directly to the universe, but it is absorbed in these molecules. And when these molecules decide to stop vibrating, they emit photons of infrared, let us say light, infrared radiation, partly up, but partly also down. And so in this way, part of the energy being emitted as an infrared radiation from the ground is in this process returned down back to the ground. And the Earth has the atmosphere approximately like today, approximately 2.4 milliards or billions of years. So the Earth has greenhouse effects approximately 2 milliards of years. Without it, it will be in our geographical latitudes for approximately 35 degrees colder than it is with greenhouse effect. That means that during summer, we would have some -5 degrees in average in Slovenia, and during winter we would have some -40 degrees centigrade. Imagine how nice would that be. So thanks God we have a greenhouse effect. Yeah. The problem with greenhouse effect is that it has increased in last 100 or 150 years. Via a very clever method, we have a possibility to look far into the history what was on the Earth. Namely, almost all elements on the Earth exist in different isotopic as a different isotopes forms. For example, oxygen, most of the oxygen is oxygen 16 with 8 neutrons and 8 protons in the nucleus. There is some oxygen 17 and also some oxygen 18. And hydrogen, similarly, there is hydrogen 1 and hydrogen 2, which is called deuterium. So from these forms, nature can produce different waters. Normal water, H1 and O16, or little heavier water, H1, 1H2, and O16, or even heavier water. You have heard that during the Second World War, Germany tried to extract the heavy water on the Norwegian coasts for their nuclear program, and the Norwegian guerrilla tried to prevent them to do that because they needed it for the so-called heavy water. Heavy water they needed for the Heisenberg's nuclear program. This helps us to understand what was the climate in the past, namely, in general, heavier matters cannot evaporate very easily, while lighter matter evaporates easier. So, to evaporate heavy water, you need, in general, more energy, higher temperatures. For evaporate lighter water, you do not need so much energy. You can have slightly lower temperature. So in warm periods, a slightly greater percentage of heavier water was evaporated than in colder periods. And this water was then advected with the winds to some distant areas. There the clouds formed, the water fell down and was accumulated. If it was on Greenland or on Antarctica, it was accumulated in a new fresh layer of first of snow, and then when it transformed of ice. So drilling through ice and putting out the samples of ice, we have the possibility to look upon the isotopic structure of that ice. And in the parts of that ice column which contain more heavier oxygen, for example, tell us that when this ice was accumulated there, it was warm. These are the records from the ice core of Vostok. It's close to some Russian expedition area. And here you see the percentage of the heavy oxygen. And you see it went up and down, went up and down. This is today, this is 400,000 years ago. So we can look upon the climate of 4,000 years ago. This is, and this graph is the temperature in comparison to the contemporary temperature through the history. And you see, temperature was rising, then it fell down, it rised again, it was falling down with some perturbations, it rised again, but down and up, and down and up, and down. So we are now going down, in spite of the neglecting the anthropogenic effects. This is natural. How can this be explained? At the start of the Second World War, a Serbian mathematician and astronomer, Milutin Milankovic, published the so-called Canon der Erdbestrahlung and the consequences of it upon the Ice ages. He namely got the idea when he was looking upon the mountains which are covered with snow during the winter, and then the snow slide in spring starts to melt, and towards the summer only the tops of the mountains are still covered with snow. And he said, well, it's the same with our planet Earth. When it's cold, the ice cap extends far down from the pole, while when it's warm, it's only in the smaller polar areas. And then he computed the astronomical factors of the insolation of the Earth. Namely, the Earth does not rotate around the Sun on a circular orbit, but on the elliptical orbit. And even more, this elliptical orbit is turning around slowly. The inclination of the axis of Earth's rotation against the ecliptica is also slightly changing from the 22.5 degrees to the 24.5 degrees. Now we are at the 23.5 approximately. And also, if you imagine this rotating Earth as a, how is it called? If you turn something like that, if it's spinning, and when it slows down, it starts to make such a crazy turns, which are called the precession. So it also precesses. Milankovitch calculated all this, and he got the insolation of the Earth, the curves of the insolation of the Earth for the history of the Earth. And amazingly, each peak of the higher insolation corresponds to a certain peak of the higher percentage of the heavy oxygen amount in the ice. And by this, by drilling into the ice, many years after his death, Milankovitch got his satisfaction, or his son got his father's satisfaction. These data are available. You can plot them. These lower are not. This data I added personally, but these data are available. You can plot it by yourself if you want. Now, for the last 1,000 years, we have some measured data in red and some so-called proxy data in blue. What does proxy mean? If it was a hunger in Europe, this was, of course, recorded in some almanacs. It was also recorded if the wine was excellent. It was recorded if there was a lot of wheat on a certain year, or it was a poor year. So these are very different proxy data from which we can reconstruct the temperature in the last 1,000 years. And you see that it was more or less constant with ups and downs. Here you see it was cold. When it was the Flemish painting school most prosperous? 1700, huh? 1700? So here somewhere. On Flemish paintings you see that people are skating on the frozen channels of Flandria and Brabant, etc. Today no one is skating there. Do the channel freeze?
Of the rivers?
Yes.
Of the no.
No.
Exactly right.
No. So this is also the proxy data. Flemish painters. And it was going up and down when it started some 150 years to go up with a certain diminishing period during the mid of the previous century, but now it's going up. And this is for the instrumental era. The modern data you can find or on my USB stick, or on the CD or on internet. And it will be your duty for the seminar. So, the last ice age ended some 15,000 years ago or 17,000 years ago. Some 10,000 or 15,000 years we have enhanced greenhouse effect. Not enhanced greenhouse effect, enhanced temperature due to the Milankovitch's effects of insolation. Namely, some 17,000 years ago, the level of CO2 rise from 200 ppbs to 300. So it doubled. And approximately at that time, the Homo sapiens was able to push the Neanderthals away. And some 5,000 years later, the first known civilizations appeared in the Babylonian area. So previously, the Homo sapiens and the Neanderthals tried to catch only something to eat. They were not able to construct nothing. They were walking around and looking, is there something not to die? This was the main preoccupation. After the temperature rised, it was the time for also to think about. This is upon the natural causes of the temperature. About the ozone. Many people have the impression that greenhouse and ozone hole are things which are coupled. In fact, they are not. Also, ozone hole is a natural phenomenon. You see, this is the image of the ozone concentration in so-called Dobson units around the Earth, higher concentration in mid-latitudes, spots of higher concentration in mid-latitudes, and lower concentrations in the polar areas. Ozone is a nice ozone and the bad ozone. Nice ozone is the stratospheric ozone, which is a shield against the ultraviolet part of the solar radiation, which is of course harmful. By heating the molecule of ozone and splitting it into two parts, in two atoms of, by heating upon the molecule of two atomic oxygen and splitting it into two atoms, that photon of ultraviolet is absorbed. And this is the way how stratospheric ozone helps us to live. Of course, some mutations are necessary for evolution. So sometimes some cell should be manipulated and the genetic structure should change. Without that, there is no evolution. But please, should that not happen upon my cells? People were always trying to escape the strong solar radiation by ladies were wearing the parasols, umbrellas, nicely decorated with the lace, etc. And it was modern to be as pale as possible. Until the Australians invented that dark brown is nice, some 50 years ago. They certainly were able to tell everybody in the world, yes, you are not nice, you are pale. We are nice, who are brown. And of course, the consequence of that is the strongly elevated incidence of the skin cancer, which now everybody knows. So now, please, ladies, try to buy a nice parasols. It will be modern in 5 years again. How much ozone do we have in the whole atmosphere? If all ozone from the whole atmosphere will be collected and put down to the ground and pressed to the pressure of 1000 millibars, it would make such a layer. And this is 300 Dobsons. So 1 Dobson is 0.01 millimeters of oxygen at 100 millibars. Nowadays, Dobson was measuring it very cleverly. He started in Spitzberg Islands in 1920 or approximately like that. Nowadays, ozone is monitored from the satellites downwards. And you can get the fresh ozone data on different internet sites. This one is American. This one is DLR Oberpfaffenhofen, Bayern. And you can get such pictures. This is some old story. You see a lot of ozone, a lack of ozone, a lot of ozone, a lack of ozone, a lack of ozone. Yeah, it is in March. It was 4th March, 5 years ago. 6th March, it was completely different. You see. 2 days later. So it's not only photochemistry, it's obviously also the weather. With winds, the ozone is transported. Also stratospheric. There is also movement of the air also in the stratosphere. And 27th of March, it was so. So if we go back from here, 2 days and 20 days. So the low ozone concentration is not only the story of the polar areas. It can happen also somewhere else. What is the mechanism? The photon, ultraviolet photon, hits the molecule of 2 atomic molecules of oxygen and splits it into 2 different atoms. One of the atoms, with the help of some other molecules which works as a catalysator, forms a molecule of ozone. And it can happen that this molecule of ozone is again hit by a photon, again split into 2 atomic molecule of oxygen and again into the 1 atom of oxygen. But as this is unstable, it very quickly is recombinated again to ozone. And at the end, this ozone can react with the other atom of oxygen to form 2 molecules of oxygen. So at the end, the balance is 0. Please.
So in your equation 4, there should be a factor 2 for the
Aha.
2 times the
Yeah, yeah. So as regards the equations, it should be slightly corrected. The balance is 0. So again, we get the 2 atomic oxygen. But the side effect is that we have some oxygen always present. So this is per partes, first process, second process, third process, and fourth process. We have a balance at the end, but we also have some 3 atomic oxygen, which is ozone, which is beneficial. We saw that it is not only photochemistry. Also the stratospheric flow is essential. Here we have some animation, you see, day per day. You have seen it. These are the 5th, the 6th, and the 7th of March 2002. It looks like moving cyclones and anticyclones, the weather patterns. Sometimes some very strange things happen. You see here above the northern pole the area of a polar vortex turning in this manner, and in the middle of it here the temperature is below minus 80 degrees Celsius, closed circle. The 17th of February 79. 17th. On 26th, the temperature here above the pole is approximately, this is, what color do you see? Yellow. Minus 40, approximately. So the temperature change of 40 degrees in 10 days. It is not possible to happen by photochemistry. It is clear from this image, we meteorologists are very familiar with such a isolines. This previous vortex split into the 2 parts which moved away from polar regions, and the air from the subpolar regions invaded the polar area. So it was a transport of much warmer air in the stratosphere on the 23 kilometers high in the atmosphere. This is 23 kilometers approximately high, and so the air invaded the polar area. So this was the so-called weather process, not photochemistry. And this is the record from Tromsø. So it was in November, December, January, cold, 210 or even 200 kelvins. Then the temperature jumped for some 40 degrees, but also the amount of ozone increased rapidly from approximately 250 dopsons to 470 or 60 dopsons. It cannot happen with photochemistry so quickly. It was the transport of ozone. Only shortly on the anthropogenic part of the story, the chlorofluorocarbonates were used in refrigerators in producing the artificial foams, etc., because they have a very low not melting, evaporating temperature. And in freezers or in other devices, these chemicals were used, but occasionally when it was some leakage of these gases, they were slowly diffusing into the atmosphere and came up to also to the stratospheric elevations. And what is also important, stratosphere is in general cloudless. That's why pilots of airplanes wear the fancy schmancy dark glasses, because they always fly on the clear, cloudless, clear, sunny, during the day, of course, weather. But still there is some tiny amount of water which there up where it is cold forms some crystals of ice. And without ice, the chlorine and the nitrogen dioxide would form the acid, and chlorine would be blocked into a stable molecule and not be able to destroy the ozone without ice. If there is ice, this acid is not stable, and chlorine is released as a 2-atom molecule of chlorine thereup. And when the polar night ends and the sun starts to shine upon the polar stratosphere, this chlorine is split in the photochemical reaction into atoms of chlorine, which is harmful for ozone. Namely, what happens? Here we have this 2-atom chlorine molecule, which is split by the photon of solar radiation into the 2 atoms of chlorine. And with this chlorine, a molecule of ozone is transformed into the chlorine oxide and 2 atomic oxygen. And in this circle here, you see that we lose by 1 molecule of 2 atomic chlorine, we lose 2 ozones, and we netto get 3 2 atomic oxygens. This was the finding of Paul Crutzen, who got the Nobel Prize for that. And after his discovery, the chlorine and the bromides were no more used for the purposes which were used for before that. The whole reaction is here repeated again. What happens? The netto effect is that we are losing ozone, and the problem is that chlorine, if we go back, chlorine after destroying the ozone, is returned back for destroying another ozone molecule, etc., etc., etc. And it will last approximately next 100 years, that all chlorine will be in a certain way used by binding it into a stable compound, for example, with nitrous dioxide. This is about the anthropogenic effect as regards the ozone hole story.